is called a characteristic equation for a reason, 1 plus kgh. And kgh on its own is known as the open loop transfer function. 1 plus kgh is the denominator of the overall transfer function. You need to you need to distinguish between the overall transfer function and the open loop transfer function. So kgh on its own is known as the open loop transfer function. But root locus diagram is here, is written in blue here. The root locus is the path taken by all roots when they are traced out in the complex plane when the parameter k is varied from 0 to infinity. See, when k is equal to root locus tell us the location of all roots on the complex plane when k is varied from 0 to infinity. Why is that important? We are going to talk about the usage of root locus diagram after we learn how to draw the root locus diagram. We're going to delay that discussion. So here, kgh on its own is known as the open loop transfer function. Now let's go back to the question. See the question here. This is for k is equal to 4. We want to verify that a point on the complex plane, a point S1 with -1 plus j is one of the roots when k is equal to 4. In fact, this is just one of the point on the root locus. K will be varied from 0 to infinity. K is equal to 4 is just one of the point. But all points on the root locus must satisfy the angle and magnitude criteria. I have my mouse today, and my mouse is working properly. See? Every point on the locus must satisfy the magnitude and angle criteria. The magnitude criteria says that the magnitude of kgh must be equal to 1. Of course, this is obvious from the characteristic equation. See, 1 plus kgh, you bring 1 to the right-hand side, and then you have kgh equal -1. The magnitude of -1 is 1, and the angle of -1 is plus and minus 180. Right? So the angle must be the angle of open loop transfer function. If the point is one of the roots, the angle must be plus and minus 180, and the magnitude must be equal to 1. So let's go back to the question here. So the question here wants us to show that using the magnitude and angle criteria, that this point is one of the roots. All you have to do is substitute this value in the open loop transfer function, and then to see whether the magnitude is 1 and the angle is 180. It is as simple as that. So I don't have to write a lot today, so my note is already self-explanatory. Okay, let's go to the final example. Okay, here. Okay, so using the magnitude and angle criteria, we want to show that a point -1 plus j is one of the roots. So when k is equal to 4, so your first task is to obtain the open loop transfer function. The open loop transfer function is kgh. So kgh is just, since our h is equal to 1, so kgh is just equal to k divided by s squared plus 4s plus 6. So this is the open loop transfer function. But here we are given that k is equal to 4. We want to see when k is equal to 4 is this is one of the roots. All you have to do is substitute the value of k, substitute s, and then see whether the magnitude is 1 or the angle is 180. So now k is equal to 4, substitute k is equal to 4, substitute s using this point -1 and j. So you substitute, this is s squared, 4 multiplied by s, 6, and then you simplify that, you get that expression. So the magnitude is given by 4 is a real number. The magnitude of 4 is already 4. So -1 plus j is a complex number. The magnitude of that is square root of the real part square plus the imaginary part square. So square root of -1 square plus 1 square, and the magnitude of 2 plus 2j is the square root of the summation of the square of the real part and the imaginary part. So this is just a Pythagoras theorem. And then now you can see that, so the magnitude is equal to 1. So this is one of the criteria that the point on the root locus must satisfy. So the first one is already satisfied, magnitude is equal to 1. And the second part is the angle of this expression, So you have the numerator is equal to 4. So the angle of 4 is just 0. 4 is just a real number, is 0. And then we have the denominator. So that is why you have a minus sign there, because when the term is in the denominator, you put a minus sign and you use the arctangent of the imaginary part divided by the real part. And then you have the second term here. So minus here is because the term is in the denominator. Again, you use the triangle, the real part divided by the imaginary part, and then you just sum it up all together. So you get the angle is -180. So therefore you satisfy both criteria. And then therefore we can conclude that the point -1 plus j is one of the roots of the system. Why it is one of the root? Because this is a third order system. So for third order system, you're going to have 3 roots for a particular value of k. But this is just one of them. Okay, so but we are not going to go through all this tedious argument and computation when we want to draw the root locus diagram. There is it has been developed, the root locus diagram, the drawing of root locus diagram procedure has been established. All we have to do is just follow how we can draw accurately the root locus diagram. See, the root locus procedure has been outlined here. I know it is a lot. Okay, you look here. It is listed the root locus procedure: 1, 2, 3, 4, 5, 6, 7, 8, 9. I know it's a lot. I completely understand that, but there's no way around this. There's no way around this. You need to embrace this root locus, this 9-step of drawing of root locus. You need to embrace this. You're going to earn 20 marks from this alone. 10 marks from your test, and then another 10 marks from your from your final. I'm not going to read one by one. We will come back to this. I'm just going to explain this using an example. Okay. The first thing we need to do is we need to clear the term here. See, poles and zeros. These zeros will cause a lot of trouble, especially when you just hear me talking without having a face-to-face interaction. It's going to sound the same. Zeros and the numerical value of 0 sound just the same. So let us clear things out about the terminology that we are going to use. Okay, so okay, I'm done with this. Okay, so let's open our new notes today. Okay, so I have uploaded this new notes to your e-learning. This is already week 7. Week 7. We are halfway through. Okay, just open that. Okay, so this is already in your e-learning. We need to clear things up here. The terminology that we are going to use. Okay, so 1 plus kgh is called the characteristic equation. Kgh on its own is known as the open loop transfer function. So when we are drawing the root locus diagram, the root locus diagram that we are going to draw is the root locus diagram of the closed loop system. See, 1 plus kgh is the characteristic equation of the closed loop system. We are just using the open loop transfer function to help us draw the root locus diagram of the closed loop system. See, there's a confusion there already. One is the closed loop system, one is the open loop transfer function. Let me say that again. What we are drawing, yeah, I had a bad feeling about this. I know. What we are going to be drawing is the root locus diagram of the closed loop system. Make no mistake about it. But we are using the open loop transfer function kgh to help us draw the closed loop root locus diagram, because 1 plus kgh is the characteristic equation of the closed loop system. But 1 is just a constant. So all we have to do is pay attention to the open loop transfer function, and then we can draw the root locus diagram. See, 1 is just a constant. It has no bearing on the root locus diagram. It's just a constant. All right, so there's another terminology that we need to clarify here. See, the open loop transfer function kgh can be written in a form of factor. The numerator can be factored out and the denominator can be factored out. So this is known as the zero pole format. So when you write the open loop transfer function in this format, so this is known as the zero pole. What are the zeros? What are the poles? So zeros is the name given to the value of s that will make the numerator equal numerical value 0. See, I want to distinguish between numerical 0 and the name given to that value. So Z1, Z2, Z3 are known as 0. Their numerical values not necessarily equal to the value of 0, but the name given to that is called the zeros. So from now on, I will make a distinction. When I say 0, I mean this Z1, Z2, Z3, so 0. So numerical 0, I will say the origin. When I say the origin, meaning that the origin of the complex plane. Sometimes I say 0 for that as well. But I will try to make sure that when I say 0, it means that the value of this Z1, Z2, Z3. So when I say poles, is the value of P1, P2, and P3. Those are the poles. All right. Any question? Is that clear? I know it is a lot. Don't worry too much. Don't worry too much about this. We'll get this. Okay. So now, when we want to draw the root locus diagram, all we have to do is follow the 9-step outline in the notes. This 9 outline. See, the first step is locate the poles and 0 of the open loop transfer function and plot them using X and O's. So that's the first step. You need to identify the poles and zeros of the open loop transfer function. Then the root locus on the real axis lies in the section of the real axis to the left of an odd number zeros and poles and 0. So the loci begin at the pole and end at zeros. If there is not enough 0, then the loci will end at infinity along asymptote. I'm just going to talk about this 1, 2, 3 first. Okay, so let us look at an example. I'm going to skip example 12. We are going to go straight to example 13. Okay, draw the root locus for a control system with open loop transfer function given as below. So this is already open loop transfer function. Now I'm going to go to my whiteboard. Okay, so we are given this open loop transfer function. So draw the locus for a control system with an open loop transfer function given as k divided by s plus 2 and s plus 4. It is already written in zero pole format. Now let's go to our 9th step of drawing the root locus diagram. Okay, so the first step here says that locate the pole and zero of the open loop transfer function. Okay, so there's no zero. So this is our open loop transfer function. There's no zeros. There are two poles. Poles at -2 and -4. Okay, so there you have it. There's no zeros because you don't have s in the numerator. You can only have k, and you have poles. You have two poles at -2 and -4. Now let's go back to our procedure here. So then we already identified poles and zero, and then locate the pole and zero and plot them using x for poles and o for zero. We need to plot that. Locate the poles and zeros and plot them using x for pole and o for zero. Since we don't have any zero, so we don't have to plot for zero. We only have to plot for poles. We have two poles, one at -2, one at -4. Okay, so you put x there at -2 and -4. So now, so we are done with this first step. Locate the poles and zero of the open loop transfer function and plot them using x and o for zeros. O for x for pole, o for zero. Okay, that's the first step. The second step, root locus on the real axis, we are talking about on the real axis, lies in the section of the real axis to the left of odd number of poles and zero. Now we are talking about on the real axis only. So this is the real axis. On the real axis, the root locus exists to the left of odd number poles and zero. So you start from the right. So there's the first pole, which is odd number pole. So there is the second pole, which is the even. On the real axis, locus only exists to the left of the odd number poles and zero. So to the left of -2, you're going to have the locus. To the left of 4, you don't have a locus because this is already even. Let's read that again. The root locus on the real axis, we are just talking about on the real axis. On the real axis, root locus lies in the section of the real axis to the left of odd number poles and zero. So this is the first one, which is odd. So to the left of that, we're going to have a locus. So this is even. The second pole, it is even. To the left of that, we have no root locus there. So we know that in this region, you're going to have a root locus. So I'm going to draw with a red line. Okay, so by rule number 2 here, so we can identify that on the real axis, that section is going to have our locus. Okay, so that's the second step. There's nothing to it. See, everything is clear. Nothing to it. There's nothing to worry. Don't worry about it. Okay, now let's go to the third guideline here. The loci begin at the poles and end at zeros, or zeros at infinity, along asymptote. Since in this example we don't have any zeros, so therefore when you have two poles, you're going to have two locus, because the locus is going to start at the pole and it's going to finish at zeros. But since we don't have zeros, so we're going to have, so our locus is going to end at infinity along asymptote. Somehow our locus is going to branch out and then end at infinity. The loci begin at the pole. See, the loci begin at the pole and end at 0. If we don't have zeros, then it's going to end at infinity along asymptote. So meaning that here, the locus start at the pole going from -2 is going to the left, from -4 is going to the right, and finally it's going to branch out and go to infinity. See, the locus is going to start at -2 and go to the left. And another locus start at -4 and go to the right. And somewhere it's going to branch out and go to infinity, because we don't have zeros. We don't have any zeros. Okay, let's go to our fourth. So since we said that our locus is going to end at infinity, so we along asymptote we need to find the asymptote lines. So the number of asymptote is equal to the number of pole minus the number of zeros. So in our case, we don't have any zero, so we have p is equal to 2. The number of pole is equal to 2. Therefore, we're going to have 2 asymptote. And then the asymptote angle can be computed using that expression, 2r plus 1 multiplied by 180 divided by p minus z. In this case, since we're going to have 2 asymptote, so we're going to use r equals 0 and r equal to 1. Let me go back to my okay. All right, so the number of asymptote is equal to the number of poles. We have 2 poles, and the number of zeros, we have no zeros. P is the number of pole, Z is the number of zero. So we have 2 poles minus no zero. So we need to find 2 asymptote line. So the asymptote angle, sigma A, asymptote angle can be computed using the expression given in the guideline. 2r plus 1 multiplied by 180 p minus divided by p minus z. Okay. So use r equals 0. when r is equal to 0, so 180 divided by 2. When r is equal to 1, you get this is the angle in degrees. So this is the angle that our asymptote line is going to follow. But where does it intersect? So we can compute another value here. The intersection of asymptote. All asymptote intersect the real axis at a single point. So this is called the intersection of asymptote. We can use this formula. So the intersection of asymptote happens at the summation of pole minus summation of z, summation of pi minus zi divided by p minus z. Pi is the value of the individual value of the poles. Zi is the individual value of the zeros. P is the number of poles. Z is the number of zeros. So we can use that formula. So the pi is the value of individual poles. So -2, -4. We don't have any zeros, so minus nothing there. So the number of pole minus the number of zero. So we have no zeros. So this is going to be our intersection of asymptote, which is going to be equal to -3. Okay. So now we know that our asymptote is going to go through -3. So this is line -3. So this is sigma A here, -3. And one of the angle is 90. So I'm going to draw the first asymptote line. The first asymptote line goes through -3 at an angle of 90 degrees. So that is our first asymptote line. So this is 90 degrees. Second asymptote line going through the same intersection, but at an angle of -270. So it's not negative, it is positive 270. The second asymptote line is going to go through the same -3 and then at an angle of 270. So it's going down. So there you have your two asymptote line. Okay, and we know that finally our root locus is going to approach that asymptote line. Okay, so we are done with this. 1, 2, 3, 4, 5. And then at what point will our locus break away? That is going to approach the asymptote line. So we need to compute where the point the locus is going to branch out from the real axis. So the breakaway point can be computed using the sixth guideline here. So points of breakaway from or arrival at the real axis may also exist. In this case, we have that point. We can compute that by writing the characteristic equation. Rewrite characteristic equation as k as a function of s, and differentiate that with respect to s equals 0, and then we can get the breakaway point. Okay, now we are going to compute the breakaway point. See, I'm running out of space to compute the breakaway point, so I'm going to erase this. I'm going to erase this this computation of asymptote. Okay, so we need to rewrite the characteristic equation as k is equal to some function of s, and then we need to differentiate that function. Okay, so now we now obtain the breakaway point. It so happened that the breakaway point is -3, coincide with the point, the intersection of asymptote. So we know that this is the breakaway point, -3, and then we can come here and finish our drawing. So this is -3, one branch going up and one branch is going down to infinity along an asymptote line. So that is our complete locus diagram. Just -3. Okay, so that is how you get your locus diagram. I know it's a lot to swallow now, but after we have drawn a few of them, then it's going to be a second nature to us. Okay, so let us take a break here and come back and we'll. Oh, okay, can you hear me? Can you hear me? Can you hear me? Can you see my screen? Okay. All right. So I guess at this point, probably you are still trying to digest what I have just presented. Let us try one more example, and then probably then you're gonna have some question. Okay, let's go to the next example. So okay, so previously we were at that, so let's go back to example 12. Okay, so here draw the locus diagram for a control system with an open loop transfer function. What the hell is going on? What the hell is going on? Cancel that. Okay, let me try. Okay, I'm losing my web camera here. Let me try again. Okay, there you go. All right. Okay, so let us go back. Let's try one more question. Example 312. Draw the locus draw the root locus for a control system with an open loop transfer function given below. So this is already KGH, which is already an open loop transfer function. The root locus that we are going to draw is the root locus for the closed loop system. We are just using this open loop transfer function to help us draw the closed loop root locus diagram. So we need to go back to our guideline. We need to go one by one. There's no way around this. Maybe step 1, 2, 3, 4, 5, 6, 7, 8, 9. But since we have gone through that once, so it's going to be a little bit easier this time around. Okay, so example 312. Draw the locus for a control system with an open loop transfer function. So note that you are already given, so you have this note on your e-learning. I've already uploaded the notes on e-learning so that you don't have to copy anything. You just follow the step-by-step description of my notes. So take note that this is already an open loop transfer function in zero pole format. So the first step is identify the pole and zero and locate them on the complex plane. Okay. So step 1, identify the poles and zeros. So here you don't have any zeros. You have 3 poles, 1 at origin, 1 at -2, 1 at -6. So step 1, identify the poles and zero of the open loop transfer function and plot them using X and O for X for poles and O for zeros. So you have 3 poles, 1 at the origin, and -2 and -6. There are no zeros. There's no zeros. So on the complex plane, you have to mark the poles using X. 1 at origin. I'm avoiding saying the word zero, so I'm going to use the word origin. So 1 is at the origin, 1 pole at origin, another pole at -2, another pole at -6. So that is step 1 in your guideline. See, locate the poles and zero of the open loop transfer function. You may get 1 point out of it. See how easy is that to get marks? You can get 1 point already just by locating the zeros and the pole. Step 2, root locus on the real axis. We are talking about on the real axis only. On the real axis, the root locus lies to the left of the odd number poles and zero. Not that one. This one. Okay. So here, this is the first pole, the second pole, and the third pole. To the left of odd number poles and zero, you're going to have some locus. Okay, so this is step 2. You have 3 poles. To the left of the first pole, you're going to have locus. So this is the even pole. To the left of even pole, you don't have a locus. And then this is the third pole, which is odd. To the left of odd pole and zero, you're going to have a locus. We are talking about on the real axis only. So this is step 2. How difficult is that? So you're going to have a locus between origin and -2. And there's no locus between -2 and 6. To the left of 6 is going to go all the way to infinity. Okay, so that's step 2. Now, what is step 3? Step 3 is the loci begin at the pole and end at 0. So it's going to start at the pole and it's going to finish at zeros. Since we don't have any zeros, therefore all of our 3 loci, see the plural of locus is loci, I don't know, loci, probably loci, I don't know. I'll get that right next time. Since we don't have any zeros, all of our three loci will end at infinity. So it's going step 3. The loci begin at the poles. So we put an arrow there. We use arrow to indicate that is where it is going. So we use arrows to indicate the locus start at the pole. See, so there's one pole at the origin, so it's going to go to the left. There's one pole at -2, it's going to go to the right, because there's no locus to the left of -2. We have another pole at -6, so it's going to go out. It's going to leave this pole to the left. So that arrow indicates that where the locus is going, where the locus starts. So the locus begins at the pole, depending on going to the left or to the right, depending on whether there exists locus to the left or to the right. Okay, and you notice here that to the left of this third pole at -6, it's going to go all the way to infinity. But here you're going to have a break point here. See, some point between origin and -2, your locus is going to break away, is going to branch out to infinity. Okay, so now we are step 3. So let's go to step 4. So now the number of asymptote. Since we have 3 poles and no zeros, the number of asymptote is the number of pole minus the number of zero. Since we don't have any zero, we're going to have 3 asymptote. When we have 3 asymptote, we have to find 3 asymptote angle. We can find the asymptote angle using this formula, and then we can find the intersection or asymptote using step 5 here. So all asymptote lines is going to go through this point and then at their respective angle. Okay, so let's compute the angle. So this is the number of asymptote, the number of pole minus the number of zero. So we have 3 asymptotes. Since we have 3 asymptotes, we need to find 3 asymptote angle. Okay, so now we need to use, since we are going to find 3 asymptote angle, we need to use r equals 0, 1 to 2. So this is our 3 asymptote angle. Substitute r is equal to 0, r equal to 1, r is equal to 2, and then here p is the number of pole, z is the number of 0. 3 minus 0, and then we have this is your asymptote angle, 3 of them. Even though we have 3 asymptote angle, we are just going to have 1 intersection of asymptote. Intersection of asymptote, all asymptote lines going to go through this intersection of asymptote. You only have 1. So you can now compute the intersection of asymptote with the real axis. The summation of pi minus summation of zi. Pi is the value of the pole, which is 0, which is at the origin, -2, -6. So these are the values of your pole. You don't have any 0, so there's nothing to minus there. Divided by p minus z. P is the number of poles, z is the number of 0, and you get this is the intersection of asymptote. All asymptote line is going to go through point -2.67 at their respective angle. 60 degrees, 180, and 300 degrees. Now you can now draw those 3 asymptote lines. Okay, there you go. So here now, this is the intersection of asymptote at -2.67. -2.67. All asymptote line is going to go through that point. So the first asymptote line at an angle of 60 degrees. So you come here, it goes through that -2.67, measure 60 degrees, and there goes your first asymptote line. all the way to infinity. Your second asymptote line at an angle of 180, go all the way to the left. This is your second asymptote line, the dotted blue line. And the last asymptote line will go through the same point, intersection of asymptote point, at an angle of 300 degrees. So we can now draw this third asymptote line. See? Now everything now become clearer. We are now at step 5 already, more than halfway through. There are 9 steps. See, I've gone through all this trouble to explain this to you. It took me all night to draw this. Appreciate that. No, forget about it. That's my job. It's my job to do that. Okay, so now we are go to step 6. What is step 6? Step 6 is just, okay, step 6, we need to determine the breakaway point. Okay. So we know that the breakaway point is going to happen between origin and -2. There's no breakaway point here because this line is going to go all the way to infinity. So at what point here that the breakaway point is going to happen? So you need to rewrite the characteristic equation for k as a function of s, and take the derivative of that equals 0, and then you can get the breakaway point. Okay, so since the locus approach infinity along asymptote, so we know that this is going to be a breakpoint there between origin and -2. Since the locus approaches the asymptote when k is equal to infinity, there exists a breakaway point between -2 and origin on the real axis here. So this sigma b here is the breakaway point. We need to determine that point at what value that it start leaving the real axis. All you have to do is rearrange the characteristic equation in terms of k as a function of s, and take the derivative of k with respect to s. Okay, so now we have that function now. Okay, so this is the k as a function of s. Take the derivative of that with respect to s, and then equal 0, and you're going to get 2 solutions, because this is now a quadratic equation. You're going to have 2 solutions. One is equal to -4.4, and the second one is -0.9. So which one that we are going to take? Since we know that the breakaway point is between 0 and -2, between origin and -2, so we are going to drop this. Where is it? So we are going to drop this -4.4. So we're going to take this as our breakpoint, -0.9. Since that point is between 0 and 0.2. So we have our breakaway point happens at -0.9. If you look at step 7, step 7 says here that the loci are symmetrical about the real axis. It approach or leaving the real axis at an angle of ±90 degrees. When the locus leave or approach the real axis, it will leave at an angle of 90 degrees, or it will come at an angle of 90 degrees, or -90. So what does this mean in our example here? We know that it's going to break away at -0.9, but it's going to leave at an angle of 90 degrees. There. So this is the breakaway point, -0.9. It is going to break at our locus is going to break at an angle of 90 degrees, going to the top, and the bottom one at an angle of -90 degrees, because the root locus is symmetrical about the real axis. So that is step 7. Okay, so what is step 8? Step 8 is not necessary in this example since the root are since there are no complex pole. Let's take a look at step 8. Angle of departure from complex pole. Since this example, all of our 3 poles are real, there's no complex pole, therefore we don't need to compute this departure angle. When we look at another example, when there exists a complex pole, then we can now compute this departure angle, but it is irrelevant to this example. And then the last step is where our locus is going to intersect the imaginary axis. See, you can see here that the locus is going to break away at that point, and it's going to asymptote with this asymptote line. At some point, it's going to cross to the right of imaginary axis. Let's go back here. Okay, so this is our asymptote line, and it's going to break somewhere at 0.9. It's going to approach the asymptote line. At some point, it's going to cross over. Our locus is going to cross over to the right of imaginary axis. So how do we compute at what point our locus is going to cross to the right of imaginary axis? So we know that when the pole crosses the imaginary axis, the system becomes unstable. So on the imaginary axis, the system is marginally stable. See, we can use that information to compute the point where our locus is going to cross the imaginary axis. So we are going to use the Routh table to determine the point of intersection with imaginary axis, because we know that on the imaginary axis, our system is going to become marginally stable. So let us go to step 9. So the intersection of locus with imaginary axis is obtained using the Routh stability criterion. So we are going to develop the Routh table. We all know how to do that, right? So let's go to step 9. So we are done with that. We are done with 7. Step 8 is not necessary. So now step 9. So intersection here, at what value this intersection happen? So we are going to use the Routh stability criterion. All you have to do is obtain the characteristic equation and develop the Routh table. So this is the characteristic equation, 3rd order, and then now you develop the Routh table. Fill in the first 2 rows using the coefficient of the polynomial. So there's 1 and 12. The second row, you go 8 and k, and then fill in the rest of the coefficient. And then for stability, you can now determine the value of k for stability, because you want all elements in the first column to be positive. So therefore, for stability, k must be between 0 and 96. So when k is equal to 96, we have our system to be marginally stable. We know that when k is equal to 96, our locus now is exactly on the imaginary axis. So you substitute k is equal to 96 back into the characteristic equation and solve for the roots. So when k is equal to 96, so these are the roots. 1 at -8, so this is the real roots on the real axis. So you're going to have 2 complex roots. So this is now, we know that the intersection of imaginary axis happens at 3.464j, one of them, and another one at -34.64j. So the locus intersect at that point. So now we can now draw our root locus diagram accurately with this information. Okay, so this is where the intersection with the imaginary axis at 3.46j, 3.46j, another one at negative 3.46j. And this is the breakaway point at negative 9. And then our locus is going to leave at 90-degree angle. It's going to cross imaginary axis at 3.46. And finally, it's going to approach the asymptote line. It's going to approach this blue line at infinity. So now we have this complete root locus diagram. There you go. All 9 steps except the step 8. In this example, step 8 is not necessary because we don't have any complex pole. I know it's quite a lot, but I think I have explained that clearly. So we have 3 locus start at every pole. So one of them going out negative 6 all the way to infinity. It is already along asymptote line, and there's 2 more locus. One start at the origin and going down, I guess, going down, and then approach this asymptote line, and the second line start at negative 2, break at negative 0.9, and go all the way to infinity along this asymptote line. All right, so now do you have any question? There's no way around that. There's no way around that. You need to embrace all the 9 steps of drawing the root locus diagram. Do you have any question? Or are you sleeping now? Everybody's sleeping, right? No, I'm not sleeping. No. Okay, I think that there's enough already for today. I'll let you digest what I have just presented. Is it approaching the asymptote line? Yes. Finally, it will never cross. For example, here that locus will approach this asymptote line, but it will never go across to the left of this asymptote line. So that is the definition of asymptote. Go to Google that. What is the definition of asymptote line? So it will just finally it will approach this asymptote line. It will not go to the left of that asymptote line. Any other question? I guess that's enough for today. That's enough already. So I'll let you digest that and go through all my computation. If there is any error, then let me know. I sometimes make some error. Okay, I'll see you tomorrow at 10. That's enough for today.